Hello and welcome to Learning with Lovo. This is episode 2 of my helicopter deep dive. In this and the next video, I'll be taking a close look at what makes helicopters fly. I'll look at the important aerodynamics and how they come into play, and how to prevent them from killing you. Let's get started. Aerodynamic effects and basic mechanics. Basics of rotor systems and controls. I'll be focusing on conventional helicopters, so we are dealing with a main rotor and a tail rotor. These two rotors are joined to one or more engines via gearboxes and drive shafts. The main rotor is made up of 2 or more blades. Their cross-section is symmetrical, so they pitch to provide lift. The blades rotate, meaning the root travels slower than the tip. Some designs compensate for this by being twisted. The root has more pitch than the tip. This is called washout. Others use a taper to reduce the lift coefficient of the airfoil near the blade tips. Some use a combination of these techniques. The effort to spin the rotor creates torque. Much as using a power drill turns the drill bit a lot and tries to turn your arm a little, a helicopter's body will rotate in the opposite direction of the rotor if unopposed. Friction with the ground will do this, but as soon as you leave the ground, you'll start spinning. For this reason, we have an anti-torque tail rotor. The tail rotor works in the same way as the main rotor and is linked to the same drivetrain, but is smaller, perpendicular, and is geared to spin faster. Often it is set to one side, sometimes within the tail itself. Its purpose is to give yaw control. If it matches the torque of the main rotor, you will maintain heading. You can increase or decrease its effect to yaw either way. Some other key points about helicopters are constant RPM. The rotor system in a helicopter runs at a constant RPM. The controls vary the pitch of the blades in order to change the amount of lift produced. However, lift and drag go hand in hand, and with an increase in lift, so too does drag increase. This would reduce rotor RPM, except that the engine is throttled in order to maintain rotor RPM. In older designs, the throttle was managed by the pilot, and good modern pilots know how to fly with a manual throttle. However, newer helicopters have a governor, which will automatically maintain a set rotor RPM by adjusting the throttle. You can also damage the drivetrain or rotor system by letting the rotor spin too quickly. This is called over RPM. In powered flight, this can be fairly rare as your governor will reduce the throttle. However, with sudden collective dumps, in severe turbulence, or during poor auto rotations, you can cause the rotor to over RPM. Over pitch. Your helicopter has only so much power available. You can pull too much collective too fast and the blade's pitch will create too much drag for your governor to compensate. Your engine and rotor RPM will droop, your thrust will drop, and then you will drop out of the sky. The only solution is to lower the blade pitch. Remove the drag and wait for the RPM to rise. Take care when adding pitch to not do so faster than your aircraft can handle. The lift equivalent has a squared component, i.e. the velocity of the air has an exponential relationship with lift. This means even a few % decrease in rotor RPM can lead to a large decrease in lift. Over torque. On the flip side, some engines can give more torque than the drivetrain can handle. This can happen suddenly with massive overtorque, or over a period of time with a more subtle overtorque. If this happens to you, it's time for a bit of auto-rotation practice, as your rotor system is no longer attached to the engine. I'll cover auto-rotation a bit later. To prevent this though, keep an eye on your torque gauges and don't let it linger in the red. Over temp. Your engine can overheat if you run it at too high of a load for too long. Once again, keep an eye on your temp gauges, as this will also kill your engine and initiate a surprise auto-rotation practice. Let's take a look at the flight controls. Collective. As it sounds, the collective changes the pitch of the rotor blades collectively. This can be equated to a power lever, and in some aircraft, such as the Chinook, it is literally called the power lever. You pull it up and the pitch increases collectively for all blades. This will give more thrust perpendicular to the rotor disc. This will create more torque and make you yaw to one side, as well as making more work for the engine. Yaw pedals. Pedals are like a collective for the tail rotor, collectively changing the pitch of the tail rotor blades and therefore its thrust. This will apply or remove a yawing force and more or less of a small sideways motion. Cyclic pitch changes. Simply put, the cyclic tilts the rotor disc. It causes the rotor at a particular part of the rotation cycle, hence cyclic, to pitch more, and at the opposite point, pitch less. Forward cyclic tilts the entire rotor disc forwards. Left cyclic tilts the discs to the left, and so on. Mechanically, forward cyclic actually pitches the blades on the left side of the rotor in a counterclockwise rotating rotor system, due to the effects of gyroscopic precession. which means the blade doesn't reach its full upwards deflection until 90 degrees later in its rotation. But this is a design concern and not something a pilot needs to know in detail. The disc tilt moves the thrust vector in that direction, providing a horizontal thrust component at the expense of the vertical thrust component. Let's look at how helicopters actually fly, starting with ground effect. You may already have heard of ground effect as it occurs in fixed-wing aircraft as well. Imagine a helicopter in a free air hover. The airflow begins somewhere above the rotor disc and accelerates downwards through the disc and then off below. There is little resistance to the downward movement of the air. If the helicopter is hovering close to the ground, the downwash hits the ground and shoots off horizontally. A diversion duct is created, causing an increase in pressure. The increased pressure of the air underneath opposes and reduces the induced flow. This means the angle of attack is greater, which means the lift is increased for any given pitch setting. Factors affecting ground effect. Height. Ground effect reduces with more altitude until it is negligible, bottoming out at about 2/3 of a rotor diameter distance from the ground. Slope. On sloping ground, the air will flow away downhill, reducing ground effect. Nature of the ground. Rough ground will tend to disrupt the airflow, while crops will bend and absorb the kinetic energy, reducing ground effect. Wind. The rotor airflow is moved downwind, reducing ground effect. However, the more wind, the more you get of something called translational lift, which I will come to now. Translational lift. If we are in a free air hover in still air conditions, a certain rotor pitch will keep us hovering. The air above the rotor will be getting pulled down into the disc and pushed out below. This is the induced flow. The airflow induced by the rotor, and that combined with the speed the rotor is going around, gives the relative airflow for the blade. The angle between the rotor blade and the relative airflow is the blade's angle of attack, or AOA. The greater the AOA, the greater the lift and the greater the drag, until the AOA gets too steep and the blade stalls. Air coming in from the front, either from a headwind or forward motion, will blow across the vertically induced column of air and change it before it reaches the disc. We still have a downward component, still have the induced flow, but less so than before. So we know air moving in horizontally with the rotor disc reduces induced flow. The more the relative flow comes in from the front, the greater the AOA for any given pitch, the more lift from the rotor and vice versa. This effect is called translational lift and starts about 12 knots of air horizontally into the disc and tapers off as we pick up speed and outrun the induced flow. However, in real life, the wind will be blowing us backwards. We would have to tilt forward to either maintain hover in the wind or maintain forward airspeed. The more we tilt forward, the more the airflow actually matches and builds induced flow. At slow speeds, the tilt required is low and we benefit from translift more and more as we accelerate and tilt further. However, the faster we go, the drag on the airframe increases to the square of the speed. So more and more tilt is needed to move the thrust vector backwards to compensate. This means more air through the top of the disc and less performance. So we can see how translift really helps us when moving from hover to forward flight, but disappears as we accelerate. Flapback and transverse roll. Flapback describes how, with air moving into the disc either from wind or forward speed, the rotor will experience greater airspeed and therefore greater lift as it approaches the wind direction. Most rotor systems are hinged at the root to allow some vertical pivot. This is called flapping and is opposed by centrifugal force. As the rotor flaps up, it kills some of its AOA. As it passes being head-on with the wind, now starts a reduction in airspeed combined with reduced AOA. This takes away lift and the rotor begins to flap down. The downward motion increases AOA, and as it reaches its lowest point, it will begin to get greater airspeed as it continues around the cycle into the wind. We can see that the rotor will flap to equality, meaning it appears as if the rotor disc tilts as one unit, even though each rotor is just doing its own thing. This process results in a rotor disc tilt away from the wind direction without any input from the pilot. You will need to push the stick into the wind just to have a level rotor disc. As I said, this can happen as you transition from hover to forward flight. This will result in a forward stick motion to begin moving, then shortly after another forward stick motion to cancel out the flatback. You may have noticed that a helicopter will pitch up when you add collective during forward flight, as the increase in thrust will start to catch and flap the blade when it is fully advancing into the airflow. And due to gyroscopic precession, which is complicated, the lifting effect will increase at the front of the disc. To complicate things further, we have transverse roll, or inflow roll. I will describe induced drag in more detail next, but airflow coming in from the top of the rotor disc takes away lift from the blade. And as we just found out, through flapping to equality, we are tilting the rotor disc. If we're tilting the rotor disc into the airflow, such as in forward flight, the blade at the back of the disc has more airflow from the top of the blade than the front. We saw just now that getting the most lift at the advancing side gives the most flap at the front, 90 degrees out of phase. Now as the airflow goes into the tilted disc, we're getting a bit less lift at the back, therefore a bit more lift at the front, meaning it wants to have the most flap at one side. If you combine the flapback from the airspeed with the inflow from the disc tilt, we see the disc actually tilts back and to one side. We'll get more inflow roll at low speed and more flapback at higher speeds, but generally you'll need to push the stick forwards and towards the retreating blade side to counter it. Let's break here. In the next video we'll be finishing off helicopter aerodynamics and later on actual flight procedures. Thanks for watching, Learning with Lovo.